and it was the seesaw was essentially this, right? We had, we had the pivot point here in the middle, right? And we had the weight from one person, FG1 and FG2, right?
Yes.
What was going on over here?
In the middle, pivot point.
Force normal going what? Right? So when I draw the free body diagram, I have one force, FG1, I have another force, FG2, and I have a normal force, FN. Okay?
No force of gravity because it's no weight. There's no weight for the pivot point, correct? There's no weight for the pivot point.
I mean, there's no...
So it's not going, there's no force of gravity down.
Okay. We have assumed, this is where we're going to differ. We have assumed that the bar itself had no mass. That's what right. We're going to change that.
Okay.
I'm going to add that in.
The one where they're, it's not the one where they're basically gravity.
No, we're just talking about the seesaw, just a basic seesaw.
Oh, I thought you were talking about test.
I'm talking about the seesaw. So we've got a seesaw problem, right? Everyone here? Before we had talked about there were three forces, the two forces going down and the one force going up, right? Yes? Okay. And if I have my ruler, right? My ruler has no forces on it, but if I balance it in the middle, if I put my finger in the middle, it's going to balance, right? Yeah, I know you're like, whoa. Okay. But there are no forces, but it's still balanced, okay? But what happens though when I move my finger over here? What's it going to do? It's going to fall down, right? Okay. Unless I pull down the side. So now, but what am I fighting over here? If I have pulled this over and now I'm pulling here, what am I fighting on?
The force of gravity times the weight
Of-
past the pivot point.
The force of gravity of what?
Of the ruler.
Of the ruler, the weight of the ruler, okay? So here's the issue. When we talk about an object of uniform mass, of uniform density, right? So this is a ruler, it's meaning that it's as dense here as it is over here. Any little chunk of material is the same amount of material, right? So if I put my finger in the middle, there's a piece of material out here. This inch is balanced with that inch, right? This inch at the half a meter is balanced with that inch at the other half a meter. The inch over here at 30 centimeters is balanced with the inch over here at 30 centimeters. And I'm going inches and centimeters, right? But does that make sense? So the torques are all balancing out. If I were to close my eyes, I couldn't tell whether I'm holding the ruler like this or like this. It's the same weight. Does that make sense?
Yeah.
If I assume that I didn't feel the difference, the weight would be the same in my hand, right? So it's as if you have something of uniform shape, okay, of uniform density, you could take that ruler and you could assume that it is the same thing or equal to. It's equal to, if this ruler is going to have mass of the ruler, this is going to be equal to a point with a force of gravity of the mass of the ruler. Does that make sense? So you can assume it's just one point in the middle of the object, at the center of gravity. Rachel, are you paying attention? Because you're looking over there. Okay? So does that make sense? We're in the middle. We're right in the middle. Does that make sense? Okay. So when I think about this object, it has a center of gravity. So I look at a ruler here, and let's say I put the pivot point out here, like this. All right. If I don't put any mass, any forces on it whatsoever, I do have one. How do I draw my free body diagram right now?
Three forces on either side and one normal force on the pivot point.
Okay. I have. Okay. So.
Plus the weight of the ruler.
Okay, but we talked about. Well, you're saying the force here versus the force here, except that we talked about the idea that it's balanced, right? So, and that's a good.
That specific example in itself is not.
Right, but okay. What Gabe, you're saying there's a force on this side, and there's a force on this side, right?
Yes.
Due to each side. But remember, we said we could envision this ruler as being one point with its force of gravity out there at that point. In that case, you don't have to worry about this. Does that make sense? Because this is balanced, because this is, it's like this versus, you're saying, okay, here's the center of that, which is right there, right?
Yeah.
But the issue is really the center of this entire thing is right here. So it's really like saying the actual weight of the ruler at this distance, which is half, if this is L, then this is L over 2, right? So doing that means that you don't have to worry about this other weight on the side because it's already taken into account in this. Does that make sense? Okay. So what we have here is we have, just alone, we have how many forces do we have on this ruler as it stands? 2. What are the 2 you have? Okay, so you've got the weight, which is at the middle of the ruler, and you have the normal force coming up. That's simply it. Now, here's the thing. If my normal force is where it's pivoting, is it balanced? No, it's not balanced. So right now, I've got these 2 forces going up, and they're pushing against each other, but they're not balanced. So I have to have another force on the other side of the physical pivot point going some direction, probably down. Right? Here's F2, right? So now I can say, all right, here is going to be A, B, C, and D. You guys seeing this? Okay. So if I'm going to sum my torques, around B, say. Now, what did we learn last week? What did we learn last week about the point in which we sum the torques mathematically?
It's supposed to equal 0, so the thing is balanced.
But which point is it always going to equal 0 about?
Midpoint.
Any point. Remember how we said that I could sum the torques around A, around B, around C, or even around D, right? And the sum of the torques will always be the same. It'll always equal 0 if it's balanced, right? So the question that we're going to ask is, what amount of force do we need at F2 to balance this out? Does that make sense? So we can say some of the torques is going to be equal to, and let's just call this, let's put some numbers here, okay? So let's say L is equal to 10 meters. That means L over 2 is equal to what? 5 meters. And let's say from the L of A to B, let's call that 2 meters, okay? So if A to B is 2 meters, what's the length from B to C?
What's
3 meters, right? Yeah, because it's 5, and this is 2. It's 2 to here, 5 to here. That's got to be 3, right? So now I can do some of the torques around B. So that's going to be F. So it's going to be the torque of F2 plus the torque. Sorry, I can't write this morning. Plus the torque of Fn plus the torque of my weight. And the weight is simply the force of gravity of the ruler, right? And that, if it's balanced, is going to equal 0. Let's break it down. So torque of F2 is F2 times LAB plus Fn times LBB, right? Point where I'm at to the point I'm going to, right? Plus F weight times LBC, right?
How did you know not to factor in D?
Well, is there a force at D?
Going up?
Is there? Wait, but what? Look at my physical object. I'm asking to figure out if I'm gonna get a guy here, and he's gonna have to pull down, right? He's gonna have to pull down on this lever. I'm asking you about what that F2 is. Is there a weight over here? Is there a force over here? No, because the entire weight of the ruler has been assumed to be this point right here, right? So you could even redraw that as, you can even get rid of D if you wanted to. Yes, ma'am.
What does the equation say, like, after the equals?
Here?
No.
Here?
That's that.
Yeah, sorry, that's torque of F2. Right? And each of these I'm just breaking down, right? I'm breaking this down to here, breaking it down to here, and breaking it down to here, right? Because we remember torque is equal to force times length perpendicular, right? Everyone follow me? Okay. So if I know I'm looking for F2. Do I know my F2? No. Do I know the length between A and B?
Yeah.
What is it? 2. But is it negative or positive?
It's negative because it's to the left of the center.
Yeah, it's negative because it's to the left of the point around which I'm summing my torques. So it's F2 times negative 2 meters. Does everyone understand that point? Why it's negative 2? Okay. But just by standard, whatever point you take the sum around, any length to the right to get to the force, that's going to be positive. Anything to the left from that, and it may not be, because I'm summing around the pivot point, the physical pivot point, I can do the sum around A, which means all my lengths will be positive, right?
But if it's going that way, it's
But there's nothing going that way, right? If I sum the points around D, all my lengths will be negative.
okay.
You see what I'm saying?
Yeah.
Okay. So time plus my Fn, which is my normal force. Do I know my normal force? Don't know it yet, do I? Okay. So I'll have to figure that out. So I know my normal force. So let's we don't know that yet. Times my length of what? BB, which is what? Oh, 0. Maybe I don't even need my normal force. Isn't that cool? Right? Plus FWT. And did I give you the weight yet? No, I'll give you the, let's say I give you the mass of the ruler to be 0.1 kilogram. What does that mean that the force due to gravity? You want an exam? Did you tell me you were coming today at this point in time?
No.
So don't act surprised that I don't know you're here.
Okay.
Surprise test. Okay, you're interrupting my class.
I'm sorry.
How when are you going to take this test right now? You don't have enough time. You don't have enough time to take it right now. You're not going to finish in a period.
Can I take it in class?
No.
But it's flat.
Huh?
It's flat.
I know, but I'm just saying you don't have enough time to finish it in a period. I'm letting you know that.
Okay.
So are you going to finish it? Are you going to start it now? Or are you going to start at a different time?
I don't know.
You're coming to me.
He has a full hour.
What?
He has a full hour.
I understand that, guys. But my point is, you said you want to take the
I
30
think I
minutes.
can do it. I like a challenge.
All right, you have a challenge? Okay. The mass of the crate is 10. For number 5, assume that this bar is not moving. You're going to have questions, kiddo, and you can't answer them right now. Okay. All right. Where are you going with that?
I'm going to the library.
No, outside, right there. All right. Okay, so let's say the mass is 0.1 kilogram. What's the force of gravity of this guy?
Negative 10 times that.
So what is that? Negative 1 Newton, right? So negative 1 Newton times the length of BC, which is what?
3.
Is it positive or negative?
Positive.
3 meters, okay? And that's going to equal 0. Now I can figure out my F2, right? So F2 is going to be negative 3, but move that over. So it's going to be 3 divided by negative 2. It's going to be 3 divided by negative 2. So it's negative 1.5 newtons.
It's all going to equal 0.
So I took, this is negative 1 times 3, right? And I move that over here, so it's positive 3. Divide, that goes to 0. Divide by negative 2. So it's negative 1.5 newtons. Okay, that's F2. So that figures out, okay, that's going to help you figure out, that lets you figure out what the force down is to balance, correct?
Is that a 2?
Where?
Oh, it's 3 over negative, Or negative
Yeah, it's 3 over negative 2, right? Yeah, give me 1 second. Right? Okay. Now, we're going to do this problem again, but we're going to solve for something different. This is what you're going to have to do for your mobile, okay? Everyone cool? Can I move on? No? All right, good? Okay. So now here's the deal. For your mobile, does everyone know what a mobile is? Does everyone know who Alexander Calder is?
I'm assuming Lincoln.
You've seen all of these mobiles before? Okay. These are all really interesting, cool mobiles. So he's got a lot of really fascinating.
Wait, we're gonna make one of those?
Uh-huh.
We're gonna like
Yeah. That's what you guys are gonna do. You're gonna build this as a class, okay?
As one, like just one.
One per class. But you're gonna have little subcomponents. So you can make it look ugly. You can make it look pretty. You can make it look interesting. It's really up to you guys, and there's really no wrong answer, okay? But someone may need to be in charge of sort of the aesthetics if you want to have a specific aesthetic. But then you have to do the calculations. Calculations are non-trivial. Let's talk about this for a minute, okay? Here's the question. You have to calculate. You have to show me in your calculations. And we may even put this on the laser part. But you have to show me in your calculations how you calculate the center of gravity of the system. So let's look at this. So let's say I have my nice heavy bar, okay? And let's say I have some sort of pretty little shape. I have another over here, pretty little shape. These are really ugly shapes, but they're not that pretty. Okay? And they can be like, oh, look, I have everything, and I got little do-do-do-do-do-do. Okay? So now, this is going to have force due to gravity 1. This is going to be force due to gravity 2, right? So let's assume that we know the mass, and we'll be able to do that because on SolidWorks, we can actually measure the area, okay, and area times density. We can figure out the density of the material. That's going to be our mass, right? Does everyone know how to do that? Density and area? Okay. If I have a block of material, okay, and I know the area of this, area times the height gives me the volume, right? Let's say it's going to be centimeters cubed. I know the area, length times width, but because this is non-normal, this is not a rectangle, this shape, SolidWorks will actually calculate the area for you in square centimeters. And then you can multiply it by the thickness to give you the volume, okay? But then if we can say the material has a certain density, the density, which is equal to so many grams per cubic centimeter, right, times your volume of centimeters cubed over 1, going to give you grams. You're going to get with the mass of your object. And the mass times gravity is going to give you your force, your weight. Does that make sense? And then you'll double check it, but we have the weight. So now you have the forces on both sides. Does everyone get that? Yeah? Everyone write that down? Everyone know how to do this? Okay. Now you have the forces. The question is, here's the question. You've got your rope and a loop. Where does that rope go to balance? Does that make sense? Where does the rope go to balance? If you know the full length, and you can choose that length, L, okay, and we're going to call this distance X. All right. Now let's do the sum of the torques. Okay. What are my, if I draw the free body diagram for this thing, what are my forces on the free body diagram? I have Fg1, I have Fg2. Is that the only force I have? What's the other force I have? the rope or the normal force, and where's that going to be going? Up or down? Okay, so I'm going to call this the force of the rope. You can call it the normal force, either ways, but the force of the rope coming up, right? It's a reaction force. These forces have to equal out, don't they? If my thing is going to balance, then my sum of the forces in the y are going to equal Fg1 plus Fg2 plus F of the rope. I'm going to call it Rp, so I won't confuse it with friction. And that's going to equal 0. Does that make sense? Yeah? So you can determine how much that's going to be. You could also do a sum of the torques equation, right? So sum of the torques. Now, you can calculate FRP if you wanted to, right? But let's say you didn't want to do this step. Let's say you didn't want to calculate the force of the rope. Where would you balance your torque around? Where would you want to? Where would you do the sum of the torques around? Where? The center, like the center here, the center of L.
Center of one. Wait.
That would be L over 2. Right? You want to do it at L over 2? Okay. So just like with the seesaw, right? You have to do your sum of the torques, right? You're balancing. Right now, if this is the seesaw, where's the physical balance point? Where's the physical balance point? The middle? The rope is the physical balance point, right? The rope might be in the middle, but if Fg weighs more than if Fg2 is more than Fg1, it's not going to be in the middle, is it? You follow me? So the middle isn't necessarily where you're going to, it's at that physical pivot point is where it's going to balance from, right? Those two weights are going to balance around those two pivot points. So if I were to draw the sum, and let's call this point A, point B, and point C, okay? Let's do the sum of the torques around the physical balance point, which is point B. What are my torques? Torque of what? Torque generated from what? Fg1 plus the torque generated from what? Fg2 plus the torque generated from what? The rope. Guys, this is going to be in the final, so you need to know this. It's not just for the project. It's going to be in the final as well. And that if the system is balanced, what is that sum of the torque going to equal? 0, right? Now, let's break it down. Torque of Fg1 is equal to what? Okay, which is, so yeah, so length A, which is going to be, is it going to be a positive or negative x? Negative x, right? Okay. Plus Fg2, which is what? The torque of Fg2 is? L minus x, right?
Wait, are these F's negative?
They're all going to be negative. Yeah, all forces will be negative. All right, let's do it this way. I'll say, well, let's do.
Like I'm just at, like.
No, I know. I'm changing. I'm sorry. I'm kind of skipping steps. I don't mean to do that. Let me go back and do this. Let's do this. Let's just say Fg1 times L A to B, right? Or let's even say B to A, so we're clear about the orientation. So L B to A. Fg2 times L B to C, right? Plus FRP times LB to B, right? Equals 0. Does everyone see that part? Okay. I'm going to shrink this puppy down. There we go. Okay. Siri, I didn't know Siri was taking my class. Hi, Siri. I don't have a grade for her yet. Okay, so let's assume that we knew the masses of each one. Okay, so Fg1 is going to equal, let's say it's going to be 5 newtons. And let's say Fg2 is going to be 7 newtons. Okay, so here's what we do. So we're going to put Fg1 is going to be what? Negative what? Negative 5 newtons times a negative x, right? Because the length from B to A is x, but negative. Follow me? With me? Okay. Plus FG2, which is negative 7 newtons, times a positive L minus x, right? Correct? Plus FRP LBB, what's that going to be? What's LBB? 0, plus 0, okay? So now, let's do this. Let's multiply stuff out. So now I have, and let's assume that my L, let's assume I give you my L. I've got to give you L. Let's say L is 10 meters, okay? So we're going to say 10 minus x for L, okay? So it's 10 minus x, right? Yep. Okay. So that's going to be positive 5x, right? Minus 7 times 10, which is minus 70, minus 7 times minus x, which is plus 7x, equals 0. Yeah? We there? So now if I solve for that, so I'm going to say 5x plus 7x equals 70. Right? And now that means it's 13x, right? 13x equals,
12x.
that's what I said, 12x. 12x equals 70. So x is equal to 70 over 12. So 70 divided by 12 is equal to 5.83 meters. 5.83 meters. So that is that's going to be 5.83 meters from that and it's going to be, it should be a negative, right? Because it's going to be that from that direction because it's really from A to B, right? So that's the position where your string has to be balanced. Does that make sense? Okay. So I'm gonna give you a problem to do, and you guys are gonna do this. And we're gonna do this you're gonna do this for the mobile. So you set them up. Now here's the thing. That's wonderful. Okay. So that's one thing. But now let's think about what this more complex mobile is going to be, right? Let's say it's a mobile like this, and then another mobile like this, right? Let's say we're hanging down, and I've got another bar here. Like this. And I have another bar hanging out over here like this. Right? Then from that, these are different mobiles itself. So this is going to be a mobile here, and a mobile little section here, right? And you're going to have maybe this, like this. And you're going to have like this. Right? And then you're going to have something over here. You're going to have something right here, right? So if you look at all of that, that's all from one big point. So there's a point, there's a point, there's a point, there's a point, 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 right? And maybe you have, your shape here, shape here, shape here, shape here, shape here, here. I'm sorry, what? You're like, okay, I know you.
No, I just.
Okay, so here's the thing, right? So all of a sudden it can go from fairly simple to fairly complex. But at the end of the day, it's the same thing, right? This upper portion here, this guy, I'm going to do it in. Let me get it in a different color. Let's do it in. That's something I want. There you go. Let's say if I did it in green or blue here. This blue guy right here. Right? That's just like doing this, 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 and this, where this is a force 1 and a force 2, right? Where the force 1 is the entire weight of this entire object. Does that make sense? So you're each going to have to pair up and do one together. Then your pair, so like you two will pair up with you two, and you'll figure out. So you're gonna do your own little piece here. You're gonna balance your piece there, and then you're gonna balance them together. Does that make sense? And you're gonna quickly start to figure out. You have to calculate where each position is, where each point is. Does that make sense? Now, you're saying, but Mr. A, that's fairly, you're all going to look the same, yada, yada, yada. I get that. So I'm going to show you how to do this so you don't have to be the same. Okay, let's say you wanted something more like this. Okay, and let's say you had the shape coming down that was something like that. Right, and then let's say you had another shape coming down that was more like this. Okay? So this is the same thing as before. It really is the same thing as before, right? You're still having the same force, but you need to look at it from this standpoint. You need to look at the length here, here, as if it was this bar like this. So this curved bar becomes this, where this is your point, left and right. You just keep it all horizontal. So your force is acting here and your force is acting in there on that length. Does that make sense? Okay, and there'll be some fudging as we go along, but I want you to show the calculations as you're doing them. Does that make sense? And so you can, and then you can have, look, you can have multiples, right? You could have another one down here if you wanted to, right? And there's just a way of, and there's a way of doing that by adding, you can just have another torque in there. And we'll do that in a minute. It's just like the normal force, it's just another torque to add to your equation, okay? All right, so what I want you guys to do in the little time we have left, okay, in the 10 minutes we have left, I want you to do this. I want you to tell me, here's my balance beam. Here's a weight. It's going to be 2 newtons. This one's going to be 11 newtons, okay? The length from here to here, length is going to be 6.5 meters. I want you to tell me, where is the center of gravity? Where does the rope have to pull to balance? That would be the new center of gravity of the system. Where does it have to be to balance? Okay? Go ahead and do that now. Take your time, work together. Do you want me to pull up the other example I had before? Do you have the notes from that? Okay. Okay. So some of the torques around point B, okay, is going to equal your negative 2 newtons. Did you do negative force?
I sure didn't do negative either
There you go. That's your issue.
for either of the forces.
Forces should be negative. Is that what the issue is, Gabe and Courtney?
How do you, okay, I know negative is to the left and positive, right? How do you know which ones are negative and positive?
Okay. So which one's what? The forces are going to always be negative if they're going down. The forces these are weights going down, right? The rope is going to go what direction? Up.
I keep getting.
Yeah, you get the same answer.
Yeah, you get the same answer. I like add them together, and then I get 0, and then I divide it out.
No, I got 5.9.
Yeah.
Wait, I'm sorry.
Okay, so I multiply. I did negative 2x plus negative 11x.
Negative 2x.
Wait, but
Okay, all right, so guys, really fast, let me do this really fast. Torque of force 1 plus torque of force normal plus torque of force 2. So that's going to be F1 times LAB plus Fn times LBB plus F2 times LBC, right? So F1 is going to be negative 2 newtons times AB, which is negative x, times negative x, right? plus, this is going to go to 0, so 0, because LBB is 0, plus F2, which is negative 11 newtons, times LBC, which is 6.5 minus x. Okay? So that's 2x, okay, minus 11 times 6.5, which is 71.5, minus times minus, so it's plus 11x, right? So that's going to equal 0. So 11 plus 2 is 13x equals 71.5. So x equals 71.5 divided by 13 gives you 5.5. Okay, cool? And that's going to be from A. From A. I can't hear you.
I have to be rehearsal.
Okay. All right, give me like 2 minutes. Give me 2 minutes. Okay, cool.
Okay.
Very good. All right, hold that for 1 second. I gotta talk to. Okay.
3 seconds. 3 seconds.
Hey, la, hey, hey, la.
I know.
I want you one consistent. I don't want you to piecemeal. Go here, go away from now, or come back, and I want all of them together. I'm here after school. I'm here after school.
Are you here?
Am I here tea period? I was here for most of the period. Alright, can I talk to you really fast? Alright. You good?
I know.
Was today.
I'm not asking you out. You gotta do this so that when we leave, and we'll go back to normal. See?
Hey, Michael.
What's up? Oh, thank you. Yeah, can you help me with
No.
you need to come to the table?
Well, I need to pick up the sign.
If you come with
I don't want to give you this. So that's a gift. Bam.
Hey, my brother, not even. I think so.
Weirdest person I've ever met.
I don't have any.
Okay, my lads.
Alright, cool. What do you need?
Get out of here as soon as possible. Right, just like ran into
Yeah, I was just gonna go this one.
Do you need something?
No, dude, get out of here.
Well, he never responded to my email. Please start taking it now because, like, I'm gonna take a bunch of time.
I understand, but I want it in one chunk of time. I don't want this piecemeal. You follow me? It's going to be one chunk. You
I
ready?
emailed you? No. I emailed you, you never responded.
When did you email?
Last night, because I was sick.
What time did you email me?
Yesterday, like during the period, I got sick yesterday and had to go home.
Oh, I saw that. I know. You understand that like I'm going solid. So what was your I saw a bit of what was your question?
I was asking if you wanted to take it today, but since you never emailed, I never looked at the stuff last night.
You should always be prepared to take it the day you come back.
I was really sick yesterday and I didn't get out of bed.
Okay, so when are you gonna take it?
I was gonna say tomorrow.
Tomorrow's the latest you can take it. What I need a chunk of time.
Well, I sent you email. How bad are the honors?
Kaylee, I understand that. I have 85 students, and I have a whole faculty to deal with, as well, along with the other things I have to get done. I'm sorry I didn't respond to your email immediately. Okay? I'm just asking, and I've stated before, when you guys are gone or sick, you have to take the exam when you get back, or schedule with me when you get back. I'm not requiring you to take it today. I'm okay with you taking it tomorrow. Okay? Okay. Now, I have one chunk of time. Are you ready to take yours? Okay, so I want you to find a space right there.
There's no chunk of time.
Then you don't do the test. No, it is zero and static. I'm sorry, kiddo. I can't do this. Like, it's unfair for you to take the exam, go away, look at stuff, come back.
Literally, I won't like.
I can't do that. It's not. It's
What
never.
you study like give us like the same problems.
You have the same problems that everyone else is having that test. They've already taken the exam. So I'm not playing the game.
Okay, I'll be
Find
here.
time. When can you do it? I'll allow you to take it tomorrow, but I need a
No.
chunk of time.
I'll take it today.
Okay.
I can take it during fourth and lunch. Have you looked at the honors ones at all?
Well, I looked at them as they came in. Anika, problem number one, the mass of the crate is 10 kilograms.
How bad was it?
I saw some people had some good answers, so I don't know yours.
Okay, wait.
Hold on. So number one, the mass of the crate is 10 kilograms. It's space and gravity. This one, this is T for torque. So this is, I want you to do T1 and T2, or this is T1, that's T2, right? These are two. Let's go. Okay? Okay. Sean.
Do you have a spare sheet of paper? Keep tracking.
Yes. Here, this is mass of the plates,
Yeah, I got
10 kilograms. Will you hear?
it. Yeah.
Sean, wait, hold on. How long are you? When are you gonna? You're gonna finish this. You're not coming here just for Flex to take this. You're not coming in and out during this Flex period, right?
I'm coming here just for
What are you doing after Flex?
going to class.
Okay, come here.
I'm gonna stay over for a few minutes if I need to.
Excuse the mess, guys. We're in the middle of projects.
You have a scrap sheet.
Yes. I knew I was getting you something, Sean. I know C, which is what the coding is based on. So.
Okay. Well, we've been trying to put it, and we plugged in our stuff. It wasn't like
It's never gonna work for us. I feel bad. People spend 5 hours